This is a 3D coordinate grid. Watch as it morphs into a new shape. Notice how the grid lines stay perfectly parallel and evenly spaced. This mapping process, which preserves the underlying geometric structure, is a linear transformation. It acts as a set of rules that defines how one vector space evolves into another, while keeping its internal logic intact. Here is a 2D coordinate plane showing two vectors, u and v. If we define a function, t, that moves these vectors from their starting space, the domain, v, to a new space, the codomain, w, it must follow a rule called additivity. If you add u and v together to form this parallelogram, and then transform the result, you get the exact same vector as if you transformed u and v individually and then added them together in the new space. T of u plus v equals t of u plus t of v. The same logic applies to scaling, a property known as homogeneity. Stretching a vector by a constant factor, c, before the transformation yields the same result as transforming it first and then stretching it. T of cu equals c times t of u. Combine additivity and homogeneity, and you get the master equation. T of c alpha plus beta equals c t of alpha plus t of beta. Every linear transformation obeys this single rule. Because of this rule, inputting the zero vector forces the output to be 0. T of 0 must equal 0. The origin cannot move. Anchoring the origin and locking in grid proportionality separates linear transformations from arbitrary, chaotic distortions. The simplest examples of this are the trivial transformations. The identity operator maps every vector to itself, leaving the space completely untouched. The zero transformation does the exact opposite, collapsing every vector in the space directly into the origin point. This diagram shows a function space representing polynomial curves. When we apply calculus operations here, they follow the exact same rules. The derivative of a sum of two curves is equal to the sum of their individual derivatives. Integrating or differentiating polynomials satisfies the master equation, meaning these continuous calculus operations are linear transformations. We can also map discrete datasets. Multiplying a matrix A by a vector x, written as T of x equals ax, is a linear transformation. This directly links the geometric movements we just saw to systems of linear equations. Whether you are manipulating continuous polynomial curves with calculus or calculating discrete data points using matrices, the governing mechanics are identical. The structural rules of linearity apply across both fields. There is a principle, Theorem 1, which states that a linear transformation is entirely and uniquely determined by its action on a basis. Look at this grid with highlighted basis vectors I hat and j hat. These vectors act as the underlying blueprint of the space. Because grid lines must remain parallel and evenly spaced, if you track exactly where I and j land, they drag the entire coordinate grid with them. Knowing the destination of the basis vectors tells you the destination of every single point in that space. If we want to find the output for a specific vector, like 1, 0, we break it down into a linear combination of those basis vectors. By stacking the landing coordinates of the basis vector side by side, we build a representative matrix. Theorem 1 provides the mechanical bridge. It allows us to take abstract geometric movements and convert them directly into computable hard data matrices. Here is a 3D vector space collapsing into a flat 2D plane. Notice the highlighted 1D line of vectors. During this transformation, every vector along that specific line gets squashed directly into the origin point. We call this set of vectors the null space, or the kernel. The flat 2D plane that remains is the range, or the image. This is the complete set of all possible outputs produced by the transformation. It exists as a subspace within the larger codomain. When working with matrices, these concepts map perfectly to the algebra. The kernel is the solution space to the homogeneous system of equations, ax equals 0. The range corresponds directly to the column space of matrix A. The dimension of the kernel measures the exact loss of information during the mapping, while the dimension of the range calculates the resulting dimensional footprint. Together, they account for every dimension of the original space. Up to this point, we have treated linear transformations as actions, verbs that move things from one place to another. But if we step back, we can ask a different question. What happens if we treat the transformations themselves as discrete objects? Theorem 4 introduces this idea. It states that you can take two transformations, t and u, and add them together to create a new transformation, t plus u. You can also scale a transformation by a constant c to get ct. This diagram plots transformation t and transformation u as individual points within a new abstract space. When you add the outputs of t and u for any given input, the resulting mapping still satisfies the additivity and homogeneity rules. The combination is closed. It continues to form a valid linear map. Because these transformations follow vector rules, they form a vector space of their own, denoted as LVW. According to Theorem 5, if the input space V has n dimensions and the output space W has m dimensions, this new ecosystem of transformations has exactly m times n dimensions. By treating these mappings as discrete vectors, we can organize them into a new higher-level vector space. This space, L of VW, has a dimension exactly equal to m times n, allowing every geometric transformation to be represented as a coordinate in a larger system of m by n matrices. When a transformation maps a space directly back into itself, where the domain equals the codomain, we call it a linear operator. The space of all linear operators is denoted as L of VV. Here we can do something new. We can compose operators, feeding the output of one directly into the input of another, effectively multiplying them. Theorem 6 guarantees that the composition of two operators, UT, is still a linear operator. It follows familiar algebraic rules. It is associative, meaning the grouping of operations doesn't change the outcome, and it distributes over addition. Take a look at this vector. It is transformed first by matrix A, and then the result is transformed by matrix B. Applying A and then B is identical to applying a single transformation calculated by multiplying matrix B and matrix A together. Operator composition is matrix multiplication. However, there is a trap here. Let's look at function space, using the differentiation operator, d, and the multiply by x operator, t. If we compute d times t and subtract t times d, the algebraic proof on screen shows the result is the identity operator I. Because the difference between dt and td is the identity operator, dt does not equal td. Applying the derivative and then multiplying by x gives a different result than multiplying by x and then taking the derivative. Unlike basic arithmetic, the algebra of linear operators is non-commutative. The exact sequence of mathematical operations alters the fabric of the space. An operator is invertible if there is another operator that completely undoes its action, returning the space to the identity operator. Theorems 7 and 8 show that this is only possible if the transformation is non-singular, meaning it perfectly preserves the linear independence of the basis vectors. In a finite 2D space, finding this inverse operator for a matrix transformation is mathematically identical to solving a standard system of linear equations to find a unique solution. But infinite dimensional spaces introduce a trap. This is an infinite sequence of polynomial coefficients. If we apply an operator that shifts every term to the right, the constant term drops off the edge and is permanently lost. Because that information is destroyed, we can never perfectly reconstruct the original sequence. The operator has a left inverse, but lacks a right inverse. True invertibility demands the absolute preservation of structural independence without any data loss. The algebraic rules governing the inverse matrix are bound tightly to the geometric reality of what is preserved and what is destroyed. If you found this explanation helpful, make sure to like this video, subscribe to the channel, comment the topic you want next. More detailed book explanations are coming soon.